Hi, my name is Stephanie Vartany, and today I will be presenting on how deep brain stimulation in treatment-resistant depression modulates oscillations above 1/f spectral noise in cognitive control networks. So major depressive disorder is a highly prevalent mood disorder. According to a 2017 study, worldwide, over 264 million patients suffer from depression, making it one of the leading causes of disease, with an estimated economic burden of over $200 billion. Cognitive control is the ability to adapt one's behavior to achieve a goal, and this is often impaired in depression. So traditional methods of treatment for depression include psychotherapy and pharmacological therapy. However, up to 33% of cases of major depressive disorder do not respond to common treatment methods and are classified as treatment-resistant depression, or TRD. Early studies on deep brain stimulation have luckily shown promise for the treatment of TRD. DBS involves surgical implantation of electrodes to deliver electrical stimulation to deep brain structures. Several studies have focused on finding an electrophysiological biomarker for TRD in hopes of personalizing treatment, but studies have so far shown inconsistent results. One tool that can aid in these results is the use of intracranial EEG recordings, which provide high spatiotemporal resolution. For our study on DBS in TRD, data was collected at Baylor College of Medicine. The patient was implanted with stereotactic electrodes for intracranial measurement across a 10-day period, where they were continuously monitored. Patients were also implanted with DBS stimulation electrodes in the ventral capsule, ventral striatum, and subcallosal cingulate. After this 10-day period, SEEG electrodes were explanted and DBS electrodes were tunneled to an implantable pulse generator for chronic stimulation. For this talk, I'll be focusing on results obtained during a cognitive control behavioral task during this 10-day period. For the behavioral task, we adapted a cognitive control task from Ritz et al. The task involves identifying the color of a set of dots moving across the screen. And so the key takeaway from this task is that the difficulty of each trial was parametrically modulated with 11 different conflict levels. So higher conflict meant that the trial was more difficult, and low conflict meant the trial was an easier trial for the patient. Traditionally, electrophysiological analysis for neural data begins by estimating the power spectral density and then dividing it into discrete frequency bands, such as delta and theta, etc. Then we compare the power in each frequency band to the baseline power to determine some kind of task-relevant spectral information. However, the power spectral density is truly a continuous function. So recent studies have shown that dividing the power spectra into these predefined frequency bands may not truly capture the full characteristics of the spectral data. So for this analysis, we instead detected oscillations with power higher than 1/f spectral noise, which is present in natural electrophysiology data. Here is an example trial to demonstrate how this method works. So remember that in general, these trials are going from the most difficult with high conflict to the easiest with low conflict. So we first calculate the multi-taper spectral estimate for the power spectral density, which is averaged across all trials for each conflict level. Then we fit a linear model to the data. In order to do this, it is necessary to first calculate the log of both the power and the frequency axes. And so this line represents this 1/f spectral noise. Lastly, we find the regions of the PSD that are significantly above this 1/f line. And so this allows us to dynamically detect frequency peaks on a more continuous scale. So this channel does in fact have a large oscillation above the 1/f spectral noise line. However, this other channel, for example, hardly has any regions with power above the 1/f line. So here we have some heat maps of where significant frequency oscillations were detected above 1/f spectral noise. The coloring indicates the difference between the PSD estimate and the 1/f line. So a brighter color means that there was a higher peak at that frequency. And each row represents the recordings from one channel. And then also the rows correspond to the same channel. So each row on the right should correspond to the same channel as the one on the left. Some channels were left blank because depending on when the task was run, various channels were rejected during our pre-processing. So the channels shown here are channels recorded from the anterior cingulate cortex, which is a key region implicated in cognitive control. On the left, we have recordings from pre-DBS, and on the right are channels post-DBS. Preliminary results show that there are differences in the frequency characteristics of these recordings in response to conflict level and DBS treatment. So in response to conflict level, there appears to be a shift in the dominant frequencies present in the highest conflict levels compared to the lower ones. Additionally, some frequency oscillations are present after DBS therapy that were not there before. Similarly, we have similar figures for channels recorded from the dorsolateral prefrontal cortex. Here, there is a spatial difference in response to DBS for which channels should present strong peaks above 1/f noise. So in conclusion, our preliminary results show that using 1/f is an important method to detect sensitive changes and oscillations across behavioral conditions, both before and after DBS therapy. This method allows us to more fully characterize spectral data that we are able to collect through intracranial EEG recordings. And so in conclusion, I would like to thank all the members at the Borton Lab for their support, especially my grad student mentor, Anusha. And I would also like to thank our collaborators at Brown for their assistance with the behavioral task and the members at Baylor College of Medicine. Thank you.